Hey everybody, welcome back to day 3 of Build Stuff. I hope everybody had a good time at the party last night. Unfortunately, being in the United States because COVID's the worst, I wasn't able to attend, but it looked like a good time. So today I'm going to be talking and introducing myself about web page speed and why it's important. My name is Bill Dinger. I'm managing director of at VMO We're a digital ad agency with worldwide offices, and unsurprisingly, our clients often very much care about web page speed. The GitHub repo, which has the slides and all of some of the code examples that you'll see throughout the deck, is available there. The web page speed. I'll also post in the chat too, since I have it open anyway. Look for questions. And if you want to follow me on Twitter, you can mainly see me ranting and raving about whatever is currently causing me stress. Last night it was the Java JDK and why does it use the machine cert store, but we're not here to talk about that. We're here to talk about his web page speed. All right, so things people would never say, right? Nobody ever says, I love autoplay videos. I don't love ads. Nobody thinks ads are good. Nobody likes how the fact Chrome using 4 gigs of RAM is fantastic. And absolutely nobody in the history of the world has ever said this web page loads too fast. Customers, nobody complains about web pages loading fast. So with that said, why is it like it is? Like, our current hellscape of web performance is that I have a 5G, I've got $1,000 US dollar smartphone, and my web page still loads like I'm back in 2001. I've spoken at Dad's office and I'm using his ISDN line for fast internet. You know, why is this the case? Why, despite all of this technology improvements, why is everything so terrible? There's a couple of different reasons, but primarily, byte for byte, JavaScript is still the most expensive resource we send to mobile phones. Nothing else is more expensive. Images, HTML, all that, easy compared with what a browser has to do to handle JavaScript. And the other thing we have is you have developers and me back in 2017 saying, you know, my page is awesome. My page would be super fast if it wasn't for all this other stuff. As the somewhat niche telephone show Babylon 5, which is having a reboot, and y'all should watch it anyway, has said, the Vorlons would say, understanding is a 3-edged sword, your side, their side, and the truth. So what I hope to teach you all about today is to understand why your pages are slow, like a deep understanding, and to kind of figure out, you know, how much of that is you, how much of that is maybe third parties, what we can improve and how we can improve it. So let's talk about that. First thing, before we can improve anything, is we really have to understand the architecture, to understand how the browser actually renders a page and like where speed comes into play. Once we understand, then we can we can measure, like we actually measure what is taking the most amount of time, and then we can start optimizing. What I often see when people get started on this journey is they don't quite understand how JavaScript works or how the page browser actually renders the page. They're not quite sure what to measure. So their optimization techniques, sometimes they can be great, sometimes they can be bad, but it's sort of a shot in the dark. Engineering time is valuable, right? Companies, I don't know if you know this, but they pay us a decent amount of money because it's so hard to find computer engineers and computer developers, software developers. So our time and resources are limited quantity. We don't have literally all day to just do anything. So when we optimize and spend time on this, we'd like for those results to be to actually be useful. All right. So that's our pattern. That's what we have to get to. And then we can see about speeding up our good old web pages. All right, let's talk about understanding the architecture. Like, how does a page actually render? So let's start with the critical rendering path. This is a Google kind of Google Web Dev performance term, critical rendering path, which is just the absolute minimum. What is the bare basic things the browser has to do before you can actually see a page show up on your phone or your desktop or whatever? There's 4 steps. It has to construct an object model. It's got to create what's called a rendering tree. It's got a layout, and it's got to paint. Those 4 things have to happen before a user can see anything on the page or anything on the browser. All right. So very first thing, we have to construct an object model. Sounds fancy. It is. It's a 2-part process. What do we mean if we take 2 different things, the DOM, HTML, and turn it into the DOM, the document object model. We have to fetch the CSS, the style sheets, and turn that into the CSS object model. So first thing, and this great diagram, you can see the path here is taken from Google. Quite a lot of resources here in Web Fundamentals. But we have to take the bytes, the raw network transfer coming over. We have to turn those bytes, which are UTF encoded or whatever, into characters. Take those characters, turn them into tokens like HTML and body and those the rest, which then are placed into nodes, and then they construct the node tree. So the very first thing it has to do a very similar thing for CSS. It has to take those exact same CSS, bring them across the network, turn them into characters, turn them into tokens, and turn them into nodes. Okay. So very first thing we do. So after the browser does that, the next thing it does, it has to create a rendering tree. So it's got these two different things, right? It's got our HTML here with all these, all the entire node tree. It's got our CSS object model, the exact same thing with all the inheritance, but it has to smoosh the two together. And that's what's the rendering tree. So we take our great div class speed over here, our DOM element here, and our CSS object model, which has, here's speed with a color of red and a width of 100 pixels, and it combines them into one thing. An important tip, the first thing to understand here, that we kind of start talking about where learning and understanding the architecture really helps you understand what can speed up, is when it creates the rendering tree, the browser only cares about visible elements. If this was set to hidden visibility none or hidden or whatever else, the browser is going to skip this step for all of those elements. Similarly, if you're using CSS like media queries, which we'll get to in later on the optimization techniques, and you have maybe specific layouts of specific widths on your browser, if you're in a different width and that it doesn't fall in that media query, it's going to skip all that as well. So, but the important thing is the browser really only cares about visible elements. Anything else is going to skip in that step. Okay. So we create our CSS object model, our DOM object model, we smush them together, we now have a rendering tree. All right, next step, the layout. So we have this great fancy rendering tree. The next thing the browser does is retrieve the device's viewport. So when I pull up my Pixel 3, because I haven't bought the new one yet, I pull my Pixel 3, I can't remember my viewport is on this, but the browser, it retrieves what the actual user viewport is. I think it's like 400 pixels by 700 pixels, something like that. Retrieves that, and then it sets the width on it. The reason it does this is so it can determine how to actually fit the pages on the actual device. So once it does that, it then uses the classic CSS box model with margins, border, padding, and places each element on the page. So we've created all this. We've created a rendering tree. The browser has retrieved the device's viewport. It set the width, and now it's laid out all the objects on the page using the CSS box model. We place it by border and margin and padding and content, and we've placed all elements relative to each other. The very last stuff it does is paint. After it does all of these things, then we actually paint something and show something to the user. In almost all modern browsers and modern phones, this will make use of the GPU, the graphics processing unit, to speed up the render. It is also the step we care about the least. Not because it's not important, it's just because of the GPU and how fast modern computers are. This takes fractions of milliseconds in almost all cases. The only niche edge case of this, if you're working in animation or something like that, you sometimes have to care about this if you have a lot of complex or super, super, super low performing browsers. Other than that, for the most part, we're A-okay. Also, before I forget, if you have any questions, and I usually paste this myself in the chat, please hit me up in the chat here with questions, and I will do my best to answer them throughout the thing in the Pine app. Thanks. Okay, so we did all these fancy things before you could see anything, but I didn't talk about JavaScript at all. So how does JavaScript fit in this measure? We've constructed the CSS object model, we've corrected the HTML DOM tree, we've created them together as a render tree, we've placed them all on our page, and then we've painted them. What happens when JavaScript is encountered? Like, how does that affect this whole process? When the browser encounters JavaScript, so when it's going through and constructing that DOM tree, it has to do 4 things. First thing it has to do is it has to download it, has to parse it, has to then compile, JIT the code, and then it has to execute it. It does it every time it encounters JavaScript when it's constructing that DOM tree. Let's take a look at all 4 of these steps. So download is network bound, right? Where to actually fetch the payload that requires bytes, and so it's maybe network bound. The other 3 steps are CPU bound. So parsing, compiling, executing the JavaScript, that doesn't matter how fast your 5Gs are. That's all CPU bound. It just depends on how fast the CPU is on the device and how fast, and that's literally it. It doesn't matter how fast your network is. Your network can be super slow. A lot of naive optimization techniques are only concerned with download, like how many bytes are coming across the wire, but that isn't super helpful in a lot of scenarios. You see here I have a performance trace. It took 250 milliseconds just to execute JavaScript. Let's see what this looks like in a practical, real-world example. We're going to open up my Gmail live. We're doing it live. I haven't looked at my Gmail. Looks great. I've got some Pine notifications. Naringa's talking to me about stuff. Fantastic. Let's take a look at Gmail. I got a Marriott notice. I got travel out of town. I will zoom in a little bit. I do realize my screen is probably a little too big, but that is okay. Okay, let's take up the developer tools. What happens with Gmail? So I'm going to go to Gmail, and we'll go over these tools in a little bit. You're probably familiar with them. I'm going to turn Gmail to fast 3G. So I'm going to throttle it to fast 3G. I've disabled the cache and all the rest. I'm going to reload my page. So fast 3G is a pretty slow experience, but I mean, it actually loads pretty decently. You can see some spinners as my chat happens, and it takes a little bit for my moon to pop in the background, but for the most part, the user experience here isn't terrible. Chat and spaces are taking a little bit, but for the most part, we're okay. If I click on this, I've got some notifications, but it all reloads relatively quick. All right. What happens though, if I go back to this and I slow my CPU down, okay? Like what happens then? So I'm going to turn CPU throttling to 6x slowdown. So my PC is pretty beefy. I've got a Core i7, something ridiculous. I've got 10 cores, 20 hyper-threading. It's pretty ridiculous. So I'm going to turn it down to a 6x slowdown. That sounds like a lot, but realistically, a 6x slowdown on this good of a desktop computer is like a medium-tier Android device. All right, now let's reload it. It seems to be taking a lot longer. Quite a bit longer. You see the slowing down to 3G, I mean, it had some impact on the user performance, but not nearly as much as this, right? Where it's still loading in, everything appears to be pretty slow. When I click on things, I clicked on that. If you couldn't see that, it took quite a while for the browser to respond. Gmail is almost entirely CPU bound. Doesn't even, most of your network fate almost doesn't even matter. It's just simply the booting up the app and all the rest that takes a while. And because Gmail is a single page, it's an app. It's all JavaScript. All right, so let's talk about the different things that impact that and why is the case. And a lot of web apps, if you're a web developer, a lot of your web apps are like this, right? It's pretty rare I get a chance to develop pure HTML. For the most part, we're developing apps or something that's interactive. It's got JavaScript on it. You may be using a framework, which we'll talk about later. Okay, so when the browser encounters JavaScript or CSS for the matter, it blocks. The browser can't do anything else because it doesn't know what your JavaScript is going to do. It doesn't know if your JavaScript is going to modify the DOM, add more CSS, move elements around, attach event handlers. It has no idea. So until whenever it's parsing that DOM tree and going through every element, it stops everything it's doing completely. Those render trees, those object stops, and it waits for your JavaScript to be done. Sort of. like a lot of things we deal with. There's some caveats to this. Let's talk about the caveats. So there is some stuff, for instance, inline JavaScript. If I just put script console log hello world, that absolutely blocks rendering and it stops. Does async? No. If you do a script async, it doesn't block rendering. Instead, it pushes it down and lets it go. Similar to script defer. Again, it also doesn't block rendering. Script doesn't head though, absolutely does. and just a normal script tag and body, it doesn't block rendering. So there are some caveats. That's why you see so much about script defers and all the rest, is because if you just do plain scripts, when it encounters it, it's just going to block rendering. It has to wait before it can actually show anything to the user. All right. So because of how important JavaScript is and how much it slows the page down and loading, why is that the case? How does JavaScript work underneath the hood? At least a little bit. So remember, JavaScript famously was made in 11 days. The architecture, which is somewhat astonishing, obviously it's gone through decades of improvement since then, but the core architecture has been remarkably the same for 20 some years now. And the JavaScript architecture was picked one of the easiest things to do, and one of the fastest architectures for handling. It's called the event loop. I mean, not just JavaScript uses it, technologies like Nginx use it, but an event loop is simply it's it's three related concepts for how things like your functions and methods get actually executed in JavaScript. JavaScript has a single thread, JavaScript has a single main thread called an event loop. Here's how it works. There is a stack, which is a list of functions and their arguments. When a function is called, it's added to the top. That's this little orange box right there. And then when it returns, whatever reasons, it's popped off the stack and it goes to the next one. The heap is largely something we don't care about. It's where objects get stored in memory. I say we don't care about it, but of course that's how you get stuff like Slack using 2 gig of memory in a tab. But for the most part, the heap is just memory management. The browser handle it. And the last thing we have is queues. Queues are a queue of messages, specifically events, promises, and functions that haven't been added to the stack yet that need to be processed later. So the event loop goes through the stack, pulls something off of this, executes it. When it gets all done with the stack, it grabs the next thing off the queue and executes it. But it does that in order. Okay. Let's see what this means in practical. Practical example. So the stack runs from the top to the bottom. Okay, so if you look at this, start me up. Okay, first thing we do is we call start me up. So this goes in the bottom. Start me up is now the only thing in the stack. Start me up though calls doing a thing, which gets added to the top, the next item. Doing thing calls calling me, which then goes above it. So the stack then executes calling me, doing a thing, start me up. Okay, it runs from top to the bottom until completion. But this is exceptionally important. It can only execute one thing at a time. And it might make more sense if you looked at it in JavaScript, like a programming language we all know. This is an example of an event loop implementation. Now, in real browsers, this is done in C, but realistically, this class we've made here, this JavaScript, is effectively how a naive implementation, 80–90% of how the event loop works in JavaScript is we just loop through, we see if there's anything to execute. If there is, we execute it, and that's about it. Else we just wait. We pop them off, we execute them, and then we keep on going with our day. And we just have a list of messages. That's our message queue to execute, which are just different functions. All right, so this interesting. So we have a plain stack of normal things. We execute each function from bottom to top, run them, and then once it's done, we flush the event loop. It then pulls new things off the queue. But an important thing to remember, remember JavaScript 11 days. This is a really easy way to implement things, but you only get to do one thing at a time. JavaScript isn't like almost any other programming language. You don't have multi-threads. You just got this single event loop that runs from top to bottom. This would be problematic for a lot of things like making network calls, all event handlers, all the rest. It'd be really hard for the browser to be responsive to the user, which is where a queue comes in, that queue. So if I go back, so here's our stack, right? Executes code from the bottom to top. But let's talk about what this queue does and how this helps browsers actually work and web pages be performant. All right, so the queue handles non-blocking code. So all sorts of things like set timeout, set intervals, event handlers, almost every single IO related thing like XHR request or just any sort of random fetch. The queue is all non-blocking code. It doesn't block. Basically, when I do something like a set timeout, So if I had to set timeout to my code, it actually places that in the queue. It doesn't place it on the stack. Similarly, if I have an event that bubbles up, those go on the queue and they don't go on the stack. And that way the browser can ensure that events and things that have to happen later can happen later without blocking that single bit of thread code, that single main thread we have. All right. So this is usually where I do a quiz. If you look at this code, and also if you're a background in non-JavaScript, maybe you're a Java or .NET person or Python or basically any other programming language that has a more traditional threading model, the first time you encounter this, you'll wonder if your brain isn't working or if you forgot the fundamentals of computers or maybe questioning the point of existence itself. But take a look at this quiz. We have making an XML HTTP request. There's some console logs in here. I'm retrieving some comments, sending it. If I catch an error, I get here, and then I got a finally. Finally, that's one. If you ran this, I'm going to flip over to the chat. Darn it. One of you is going to answer. If I ran you this, what would be the expected order of the console logs? Starting here, starting our program, what would you expect to see? Hold on, I'm going to flip over the chat. Let's see what you all say. I believe chat, folks. I have to wait like 10 seconds. Unfortunately, there's a teeny bit of an encoding delay. We're going to ponder what we know about the event loop and how it executes from stack from top to bottom, and then the queue where anything that makes a request or an event is popped over. Okay, think about that. I mean, the first one, I'll give you a hint, is starting our program. Okay, very first thing we'll see in the console log is starting our program. The next thing you will almost certainly see is out of try block. So starting our program out of try block. You're not going to see non-blocking complete because this XML, this is a request that gets tossed onto the queue. So, and then the onload happens when it finishes fetching this. You'll get the non-blocking complete. So you're going to see starting our program out of try block. And the last thing you're going to see, or the next thing you see is finally that's done. So because the finally block is going to get executed because it is on the stack and this is not. Then the next thing you're going to see is non-blocking complete because the browser, again, it's going to execute everything here. It's going to queue this onto the queue. It's going to place this, and then it's going to execute this once the stack has finished. It's unintuitive behavior, but in that way, the browser can ensure that we're not having to worry about blocking the thread while we retrieve XHR requests. It can just go on and do other stuff and wait for this to complete before it needs to actually worry about it and do anything. All right, so to reiterate, our event loop. Function calls and their arguments go on a stack unless that is doing something. And by doing something, I mean running set timeout, running an interval, making an XHR request, then those go on the queue and are processed in order as they come back and the event loop is flushed. If you ever wondered, and you'll often see this in like Stack Overflow comments, people will just throw set timeouts or set intervals in code and stuff will start working. The reason for that is because whatever they were adding to that set timeout was waiting for something else in the event loop to get finished. And so they're basically queuing it to let the event loop flush before they add their program or your function call back in. That is why that type of behavior works. Also why if you're an Angular or some other program, you see this all the time to try to get like change detection and all the rest. You're trying to basically let the browser process what's in the event loop first, and then you add your things, and then your things will process later, and the event loop will have been flushed because the set timeout and set interval get added to the queue and get processed later. All right, so the browser has to do all of these things, right? It has to download all the code, download your JavaScript, JIT it, parse it, execute it, run it through the event loop before it can ever show anything to the user. That's a lot of work. So how do we measure this? Well, good news is Chrome and Firefox both ship with some pretty good performance monitoring tools, and we can take a look at them actually right now. So I for the most part, end up using Chrome dev tools, not because they're necessarily better than Firefox's, although they are in some respects. Firefox are better than others, just because I'm more familiar with them. But not Chrome, sorry. Firefox are certainly pretty good. So let's take a look at the Chrome one. So we're going to go over to our good friend here, our good friend Gmail. So I'm going to go to performance tab up here. I've got 3 boxes checked: memory, web core, web vitals, and screenshots. I'm going to click this button up way up here, which is start profiling and reload the page. I'm not going to do any CPU throttling for right now because I want to show you what it looks like without. So it's going to take it a second or two. Basically, what this does is it reloads the page and collects a whole bunch of data for us. I'll show you that data in 1 second. Of course, it takes too long because we're waiting for it. Oops. And I clicked away. Give me 1 second. I will click back. Oh no. My favorite. There it goes. Okay. Wow, this is a lot of data. So let's start at the top. First thing I'll do, there's a timeline up here. And there's a couple things in this timeline. I'm going to zoom way in, by the way, so y'all can see. Hopefully, let me see how that looks on stream. Give it a second. Okay, it looks pretty good. Okay, so I zoomed way in just so everybody can see everything. So the first thing it gives up here is a timeline, just by milliseconds. And there's a couple bars. So this bar up here, these different colors, the purple, the orange, and the gray, is showing CPU time. It's showing frames per second, and it's showing network traffic. And down here is a list of screenshots it shows as the page renders. And then it's got the heap size, or the heap, bunch of JavaScript, where JavaScript stores all its memory, objects in memory. So if I'm gonna zoom back out, you can kind of see here that when I load this page, at the start, there's quite a bit of CPU and memory traffic, and then it dies down. There's a little burst here at 4 seconds, and then for the most part, it's been okay. And similarly, we have a burst of CPU here as JavaScript is executing, and then it kind of dies down, and everything is all right. So this is a good way to see, where a lot of the JavaScript execution is occurring on your page, where a lot of the network traffic is occurring. Quick overview of that. Another thing it does, as I zoom back out, is it gives you the Chrome Developer Tools give you this long tasks here. You can see here, these are any JavaScript tasks that take more than 50 milliseconds. So let's zoom back out. So it also gives here, I'm going to expand on network. It also gives what's happening in the network above here. So you can see here, I'm making this call. This took quite a few seconds. There's a chat, Google's downloading manifest. Just basically, this is when all the network calls are happening. It's a nice little timeline view and how long they take. So it took me 1.5 seconds to grab whatever that is off Gmail. And many of these are much smaller, different network calls it's making. All right, so we also have long tasks. So let me show what that looks like. One of the things when you zoom way in, I got to zoom back out because I got to fix. My biggest complaint about Chrome Dev Tools is it's not designed for anything but a gigantic monitor. Okay, I'll zoom back in, but I want to show you something here. So we have long tasks. So these are the first things that we usually look at when I look at JavaScript performance in browsers and why pages are loading slow. All of these indicate times when the thread loop was, or a single function call was taking more than 50 seconds or 50 milliseconds, sorry, or when the browser, in general, the JavaScript thread execution was completely booked for that time. So what you can do is you can zoom in on these. So long task, we have this thread main. Remember we talking about the event loop? Main is our event loop. So again, long tasks. I'm going to click on main. We zoom back in here. There we go. Click on main. You can see different tasks. If you hover over them, it's saying us, hey, this long task took 200 milliseconds. And this long task took 149 milliseconds. This long task took 310 milliseconds. And then it gives you the entire stack trace of what happened. So this is minified code, but you can kind of see what's going on here. So for each of these functions, like this took 178 milliseconds, this took a little bit less than that, and so on and so forth. And it gives you the entire tree of what the JavaScript events took. So here we had 2 different function calls. This one took 177, this one took 123, and it goes all the way down until you can see every single thing the browser executed in that function trace. It also will show you stuff like, if I zoom way in, and hopefully I can get myself back out. See, this is what I mean. starts to break down. It'll show you stuff like render events when it's rendering, but it gives you a good overview if you're looking at those long tasks of what your browser and JavaScript was doing and why it took so long. The other thing you'll notice is if I reran this, in the interest of time, I probably won't, just look at the time here. If I reran this under slow throttling, these would go from 240 milliseconds to like 2 seconds. Really important thing. One of the things when we're developers, when I'm developing, I'm using my PC or my Mac, that's a God box effectively. Very few users have as powerful machines as developers typically use to develop their code. So we often get this distorted view of how our page performs. But realistically, I do a lot of work with telcos and big companies who have worldwide presences. And the sad fact is not sad fact, this is reality. It's about half of the users who hit most of our pages are browsing on like a sub $100 smartphone with very terrible specs that performs worse than when I do a 6x slowdown, which I'm going to actually do real quick so I can show you. So when you consider that, you got to remember that when you're optimizing your pages, and while 200 milliseconds might not seem a lot, that's on a desktop in an ideal situation. When I'm talking about like a browser, somebody's phone on a bad network, oftentimes the results are a whole lot worse than that. And we get some really, 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 really terrible results. So you see here, I'm just trying to profile this page with 6x slowdown, which again is more like a medium Android. It's not even that bad of an Android. And it's going to take 30 seconds as opposed to 5 seconds to load the page. When it comes back up, I can show you, you get a little deeper dive into what the JavaScript was going. Also, a side note here on the Chrome DevTools is the more data you collect, the longer it takes. It's not particularly optimized. So yeah, and you can see here that these tasks that were taking a couple hundred milliseconds, they're now taking 2-3 seconds for each to load. And you can see each of the individual function calls is taking much longer. Okay, so you can see every individual one. Here's a whole tree. You can also see down here it marks again the layout, render shift. We'll get into what forced reflow is here in just a second. Okay, so that's an easy way. Well, easy. We'll get to how to make it even easier for us to tell us how long each of the individual functions in our JavaScript takes. It also gives us some other additional benefits. It adds core web vitals and some loads showing up the timeline, DOM content loaded. And finally, it also gives us, not finally, but it shows down here documents, nodes, listeners, GPU memory in this nice graph. And if I click on a single task, like this task, I'm gonna zoom in again. Let's hope I can show it to you. Zoom in. Okay, so I clicked on one of those long running tasks, and down here under the summary bottom up, you can see that this task, what it was doing, well, it took 1.5 seconds was scripting and 834 milliseconds was rendering. And if you click on bottom up, I can see each of the things it was doing. I can even sort them by total time. And this JavaScript that was executing, and you can see each of the individual functions and what took the most amount of time, 1.8 seconds to execute this. Or in particular, this styling, recalculate style, took 551 milliseconds. So another good way to look for like functions and different things that are taking a lot of time is to click on that bottom up, sort by self time, and just try to dig into which function was taking the most amount of time. So there's a ton of information presented here, and this is actually only a brief tour. Google obviously has a whole lot of resources on how to use the dev tools, but let's talk about how we can use them even more easily, or how we can instrument them a little bit. All right, all right, so those are really cool. The Chrome performance terms are amazing. And we're going to talk now about how we can enhance them and how we can also, like, that gives us a good, a sort of good view, but let's talk about how we can enhance them a little bit. So first thing is real user monitors. Like I said, when I'm doing performance monitoring or testing on my desktop, again, it's probably a lot nicer of a machine. You know, I have gig fiber here. I'm not worried about a bad network. And I mean, you know, you could argue, I guess, the United States is a developed country or not. Fair enough, based on the last couple of years. But you know, a developed country with good, stable network infrastructure and all the rest. But that's just me. I'm not necessarily a real user or a normal user for your app. So it's important to collect and measure from a wide varieties of, wide array of devices, countries, regions, network connections, all the rest. We want to collect meaningful stats and send them to a centralized analytics store for analysis. Now, there's a bunch of third-party paid tools like T-Leaf, New Relic, and Dynatrace. One of the things we'll talk about, however, is you can also just collect these, just send them to Google Analytics or whatever analytics provider is, and use those to give a performance view. And there are quite a lot of built-in events you can use. So, you could send stuff like how long these different stats take and send them to your analytics, and you can get a good indication of how your page is performing in the real world. So let's talk about some of the plain built-in ones. So some of the first ones is DOM interactive, which is misleading. DOM interactive is just, if you think of when we talked about the very start about understanding, that's just when the browser has finished parsing the document. Okay, that's all that is. It's just browser has finished, constructing the object model and doing the rendering tree. DOM content loaded. So that means it's parsing the document, the DOM construction is complete, and it's painted. In addition to that, those scripts that are marked as defer and async have also finished parsing and executing. Okay, so that's a decent one. DOM complete is all scripts and all dependent resources that they've injected and have finished downloading. So DOM complete is sort of like not just the page is visible, any injected tags have executed, all scripts have executed, and there's been no XHR requests or anything else for I think it's 2 seconds. The spec has it. We also have first paint. First paint is not what you think it is. First paint is when I go to a web page and I do I'm on, I don't know, New York Times or something, and I go, type in the browser, build stuff. First paint is how long it takes from it to replace New York Times with either a blank image or the first image it can retrieve from build stuff. So it's more a measure of how quick your servers are responding and how much the initial payload comes back as. And first contentful paint is a little bit different than all that. Even more, first contentful paint is the first time the browser renders any text or any image from your page to the user. So this one is the first time, instead of seeing a blank page, when I navigate away, it's the first time I see anything at all, any image, any header, whatever. It's the first time a user indication that something's happening on your web page. In addition to these built-in events, and the problem with a lot of these is some of these are sort of lies, which we'll get to in a bit, and Google has tried to add some new ones, and so have the other members of the W3C to try to show that a lot of these aren't very meaningful to the user. DOM interactive doesn't mean much to the user. It certainly doesn't mean the browser is interactive. It just means that you can look at the DOM, the document object model, interact with it from a programming perspective. Not super helpful for the user. DOM content loaded is usually a lie. If I go back to our performance trace we did before, I'm trying to find DOM content loaded here. You will see it showed up, if I can find it, and everything all minimized. It showed up, yeah. So you see a DOM content loaded here at 2.5 seconds. I'm sorry, at 16 milliseconds. This was from before I hit reload. The DOM content loaded here at 16 seconds, but there's still a ton of JavaScript executing after it. And depending on your app, the browser often isn't responsive and all your pages aren't loaded because other scripts might be firing in the background, other threads might be happening, event handlers might be attaching. So that one isn't particularly useful or isn't super useful. First paint can be, again, first paint is a good indication that, hey, are we having server issues? Not usually the case, but if you're taking a long time to respond to requests or DNS issues, or whatever else, first paint can be pretty important. First contentful paint is about the only one that's pretty important to the user. And that's just a good indication to the user that something is actually happening. But we can do better. So there's performance APIs. There's a whole lot of performance APIs built into the browser that we can look at. So these are under different, you can just look at the browser namespace, window performance timing, window performance mark, resource timing. What these allow us to do though is we can create our own custom events. So we can use these performance APIs to instrument our own application to see, hey, how long is my function call? How long is my React methods or whatever taking to do? How can I get some more data from this rather than that, pretty long, pretty confusing list of minified JavaScript like I'm seeing here. Right? How can I show better results? Well, this gives us the ability. So these are very high precision and very high accuracy. I think they're 100 nanosecond increments, although that has actually been turned down because of Spectre and some other CPU related rigmarole that can happen, not rigmarole, vulnerabilities that can happen. Regardless, though, we have a bunch of performance mark, performance measures that we can use to instrument our app. Take a look what that looks like in the real world. So here's a super naive, but it works example. So at the top left here, I have a function that takes in a name. And what it ends up doing, it creates a mark. We do marks and measures. So a mark is, we have a start and an end, and we measure in between. Okay, so we create a mark, create an end mark, and then you measure in between them. When you do that, that will display in Chrome DevTools. Okay, so if I look here, in that fancy little Chrome DevTools like we were shown before, instead of seeing this minified JavaScript, what I'm actually seeing is like my own custom marks I created. So here I added a mark for, hey, I'm making a network work async. Okay, well, that took this exact amount of time. You can see it shows up just nice in the browser. Or here I made a mark to see, hey, how long does it take for me to parse this JSON? And I can see it exactly right there. I mean, and the name that shows up here, just so we're clear, is whatever you pass into the function for the measure name. It's pretty cool. And that way it's really easy for us to see exactly what they show up in the Chrome DevTools. So we can easily see, hey, what are each of our functions taking? Or I'm worried about how long this is taking for users. Well, you can create a mark and it'll show up in a measure in between, 2 marks, end mark, start mark, a measure in between, see exactly what shows up, exactly how much time it took. When we talk about analytics, remember our Chrome DevTools are our real users. Well, these are just API calls off window.performance. You could then report these exact things to your analytics tool of choice, some event of some kind or whatever, and the analytics tool can surface that back up to you, and you can easily see, hey, now isn't that nice? I can see exactly how long measured JSON is taking on average for all of our users. Maybe it's worse for some users, maybe it's better for others. It's really powerful. So normally I would pop up a demo here. Let me see if the demo gods are going to work for me today. I'm not 100%. Let me sign in real quick and show what this looks like. All right. So as mentioned, I work for, oh yeah, I have a past due balance. That's terrible. Anyway, as mentioned, you know, I do a lot of work for different telcos, and add new device. This is what T-Mobile is, one of the ones in the United States, big telco. But one of the things we did here when we were building this is it's, you know, very important for us to kind of see, as a cell phone company, to make sure our pages were loading fast for our users. So we wanted to, but you know, it's a complicated page. There's a lot of JavaScript here. So one of the things we want to do is we want to add those performance marks and measures to good examples. Have a look at those minified results. We can see better results. So I'm on this. I'm going to go ahead and run a performance trace. What I did is I loaded the phone wall, which is a list of all phones and their pricing. And I hit the performance trace, capture it. It's probably going to take forever because I'm waiting for it as per international treaty. All right, let's take a look and see what this actually looks like then. So if I go, let me minimize this. There we go. Okay. So let me see if I can make this a little, yeah. Okay, let me zoom back in. Awesome. Okay, so we have the same thing we saw before. We have the, you know, long running tasks. We have the JavaScript down here, but we also now have some custom events that are showing up here. These are all the ones that we created, that we added. What we end up doing on this site is we end up creating the concept of high components, medium components, and low components. Just kind of give us a good example of, like, you know, grouping up where we want things to load for user perception related. But you can see this is a custom mark that we created. And if I zoom even more, look at the medium components, I'm zooming way in. Instead of this really cryptic, I mean, this is, again, obviously it's all, you know, minified JavaScript. It says really cryptic things. I don't know what this means. Like, this is minified code. What's happening? We added this to each of the of our components, and I can move over them and see, hey, look, it took 8 milliseconds for the cart item component to finish, or it took 10 milliseconds for the header login component to finish, or whatever NBA buttons, or UF analytics, device credit. I have the exact timings here. So I don't have to rely on digging through this. I can easily just see in the performance tools what took the amount of time. It's super handy. Then, of course, just like I mentioned, we, you know, and done this technique all over the place, but we end up instrumenting then these events to analytics. So I can see not just on my browser, but if I go into the analytics tooling, see, well, cart item count component took an average of 10 milliseconds across all devices, or maybe it's 100 milliseconds. Hey, that's something we need to investigate and spend our performance dollars fixing. Okay. Pretty cool. And the fact they just show up here without us excuse me, having to dig into the JavaScript trace and figure out what it was is a very nice, very handy. I actually do need to go buy myself a new phone, but we're not going to do that today because we are doing a talk. Okay, so that was our real site. So how do we do that, right? You know, you saw that. How do we add these? You know, this is a pretty easy example, but how do I do that in the practical real world? Well, let's talk about Angular. My favorite, definitely my favorite front-end SPA framework. So Angular, you can do it. You could add this exact code as either a a new decorator, or you could add it to the after view init. So you do something like you create a decorator that looks basically the exact same as this, as register performance. And for the mark name, you might add a decorator where you just pass in the class name, or you can add it to after view init. You just add that there. It would go ahead and handle, you'd be able to see exactly how long your top bar component took. You could also do it if you're doing React. You could add it in component did mount, again, using the same type of thing, or decorator. View is very similar, right? I can't remember what views is off the top of my head. It's not component did mount, component mounted maybe. I can't remember view off the top of my head, sorry. So you add this yourself to all these components, and there you go. You've instrumented your entire app. It's pretty handy. The other measuring performance I want to talk about is Webpagetest. Free open source project. It's kind of sponsored by Google, but plenty of other people do. It's got a great website you can take a look at. It'll run tests against your different pages. It'll save the performance traces. It'll save a ton of stuff for you. It also has standalone Docker containers, which is pretty cool because you can use those to integrate them into your CI/CD pipeline. You can pull that Webpagetest container down, maybe run it against your dev or stage deployments and kind of do those performance testing yourself. It also supports like capturing video and all the rest. Incredibly handy, and it's a free tool, which I'm not trying to sell you anything, to be clear. I'm just here I want to make the web faster, so it's a handy tool. Google also has the Core Web Vitals. Important thing about Core Web Vitals. So remember, go back to all these different events. Well, Google didn't think these were very helpful to real user world interaction. So they did they created what's called Core Web Vitals. I put helpful in quotations. Why should I care about Core Web Vitals? Because Google cares about them. What does that mean to me? Well, Google is going to start ranking your page by how well it performs in these, which means you get SEO value the faster your page is, which usually means if you get SEO value, you get more traffic, and more traffic equals dollars. Like, this has now become hey, it'd be nice for pages load faster too. If your page loads faster, it's actually a competitive advantage over your competitors. So Google uses Core Web Vitals to measure 3 different things. Largest contentful paint, FID, first input delay, and cumulative layout shift. If you go to the Core Web Vitals page, webdev.vitals or web.dev, they have more in-depth explanation of each metrics, which I'm not going to get into. We're just running short on time, but they go over what each of these means and how to optimize them. But largest contentful paint is exactly what it sounds like. It's when whatever happened on the page was viewable to the user, whenever the biggest item happened. First input delay is just how, if the page is too laggy, that'll mark a negative against you. Users hate that. And cumulative layout shift is designed to measure, we've all experienced this, and users universally hate this. When you load a page and all of a sudden like elements shift and change, or maybe something gets inserted above, or there's some ad that pops up, all that is a cumulative layout shift increase, and Google scores you aggressively terribly if you do that, which is actually okay in my book. But anyway, these have a real dollar impact. If you optimize these and have all green, Google would literally send more traffic your way. Google also pronounces Lighthouse and Lighthouse Ci. I'm not going to do a huge dig into them, but you're probably familiar with them. They measure the Core Web Vitals. They also, we talked about, they also will give you different things like time to interactive and total blocking time, just trying to show you, take those kind of more abstract metrics we were shown before and kind of give you ways to improve and increase your web page performance. They also have Google Lighthouse Ci, which is again designed to be integrated into your continuous integration, continuous delivery platform, and measure like different, like you can measure your branch and see how fast it's performing compared to like the main branch and all the rest. And again, all free, pretty easy to integrate. This talk's not about that, but if that's your kind of your role, maybe you're a DevOps engineer, you want to make your pages faster and start gating things, or at least get some insights into your deployments, I would highly encourage you to check out Lighthouse Ci. And last, we have the rail model. Oh, not lastly, but when you think about measuring performance, I want you to know the rail model, which is consider your application as it renders, as it animates, what it does when it's idle, when it's under load. We usually focus a whole lot on load, animation, and rendering. We don't usually think about idle behavior, but if your web page is if it just idles and sucks up a bunch of CPU, that can have a whole lot of terrible consequences for you. Nothing good can happen. As a matter of fact, I've got a whole lot of bad stories about how this impacts customers. But think about it this way: if your page is sucking a lot of CPU on a browser, on a mobile phone, most modern phones will then de-optimize your page or shunt resources away from it to preserve battery life, which is not great. All right, so spent a whole lot of time talking about how to measure, how to understand the architecture. How do we actually speed things up? Well, there's a couple ones. First thing I want to think is you should probably establish a performance budget. Everything costs money or time. You should probably discover what is acceptable to you. There's some handy tools for that. But first thing you would do is you want to establish a performance budget, like how many images we're allowed on the page, how much JavaScript we're allowed, what goals we're going for. And after that, you take a look at, is it just the fact that we're shipping too much stuff? Or is it the fact that is your rendering performance CPU usage is too much? And for each of those, there's different techniques you can apply. So let's talk about for JavaScript. So everybody's pretty familiar with Webpack. One of the biggest things we typically see nowadays is one of the biggest negatives we typically see nowadays is problems with shipping too much code. So you use minification, tree checking, and code splitting to kind of get rid of all that, or not get rid of all that, to ensure you're only shipping the bare minimum necessary to users. Other technique we can use, we mentioned, remember at the very start, the browser only renders what it can see. So you can use media queries in CSS to ensure that it doesn't have to care about large parts of your DOM or CSS. That we're using those media queries is an easy way for the browser to ignore huge parts of your CSS or large parts when it's constructing those object models, which speeds it up. There's Reflow. Reflow is anything that forces that browser to recalculate the entire layout of the page. So if you think about it, go to those stops, we check the document object model, the CSS object model, the render tree, and the layout. Well, Reflow is when it has to redo all that, which is a huge CPU problem. You'll see in the console, forced reflow. Many common methods, inner height, inner text, focus, scroll, will force the page to reload. Like just using inner height, inner text will force a reflow, which will really kill the execution of your page. This GIST, because this is the world we live in, but whatever, this GitHub GIST has a full list of every known API method on window and document that forces a reflow. Network optimization techniques, I'm going to us. It's a lot of nerdy stuff, but it's around using stuff like HTTP2, a content delivery network, e-tags, caching, and cookies to ensure that you're really shipping the bare minimum and it's properly optimized for your users. Service and web workers. We talked, we only have one thread. Well, actually, we have a couple other threads. Service workers are a separate thread we can use, so we can do stuff like, so it won't interfere with that main event queue, and it lets you do stuff like cache network calls or proxy network calls, or prefetch things that all won't interrupt that main thread. There's a great tool called Google Workbox, which has some good examples of this. And web workers is a good way for us to offload any CPU intensive thing. It's a whole separate network thread or whole separate thread that's not part of the event queue at all, and lets us push anything that's CPU intensive. You can think about if you have large JSON payloads, or maybe you're making a video game, any sort of business logic that's really CPU intensive, you can offload to a web worker, then you will keep that main event loop clear. However, good news, I have all of these collected into one location, because simply just going through all of the optimization techniques would suck up all of our remaining time. And really the point is, once you understand how the architecture works and how to measure it, then you can start digging through the different optimization techniques, how to speed up your JavaScript or your CSS and all the rest. And this performance checklist certainly has all of that collected into one. Got a bunch of resources here at the end. And particularly cost of JavaScript, event loop, the critical rendering path, Rails, script scheduling, all the stuff we've talked about. Google Core is vital. If you want a good talk on service workers, Jonathan Mills, who's a speaker, has done a couple good talks on service workers. This one's free. I like it. It's on YouTube. I would suggest it. I want to learn more. It's quite an in-depth topic. But thank you, everybody. I'll post a link to everything in the page. And oops, let me go back. I'll post a link to this in the chat as well if you want to take a look at digging into those additional resources. And have a great rest of your conference. I will see you all in this exact room here in about 10 minutes. Thanks, everybody.